Mercury is the smallest planet in our solar system. It has a radius of 2,4 times 10 to the 6 meters and a mass given in kilograms. Calculate the magnitude of the acceleration due to gravity on the surface of Mercury. Well, on the information sheet you have G is equal to capital G, mass of the planet, radius of the planet squared. So let's substitute in those values. 6,67 times 10 to the negative 11, it's on the information sheet, multiplied by a mass in kilograms, 3,3 times 10 to the 23, divided by a radius in meters, 2,44 times 10 to the power of 6, and don't forget to square it. And you land up with an answer of 3,7 meters per second squared. Two metal spheres on insulated stands carry these charges. The spheres are arranged with their centers 40 centimeters apart, so that's done like that. Draw the electric field between the two spheres on your answer sheet. So the first thing is that we get radial electric fields around a point charge. So, and it goes from positive to negative. So away, 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 away. Towards negative, yep. The negative PS is stronger. It's a value of 6. So I better make more lines around this negative to show that it is a stronger electric field. And then we can make some connections like that to show that they link up. But there must be that evidence of a stronger field around the negative 6. Calculate the force between the two spheres. That's not particularly difficult. F is equal to K, Q1, Q2 over R squared. We're going to just have to do our conversions of microcoulombs into coulombs, which is times 10 to the negative 6. So it's 9 times 10 to the 9, 4 times 10 to the negative 6, 6, oh, this is going to be a bit of a problem, 6 times 10 to the negative 6, and divide that all by, don't forget, a distance, 40 centimeters is 0,4 meters, and don't forget to square it, and you land up with 1,35 newtons. Then comes the tricky question. Calculate the net electric field intensity at point P shown in the diagram above. And so what we need to do is we need to start off by saying, well, what is the electric field due to the 4? And what is the electric field due to the 6? The electric field at a point is equal to KQ over R squared. So I'm going to just calculate that. 9 times 10 to the 9, 4 times 10 to the negative 6, and the distance between this charge and P is 60 centimeters, which is 0,6, and I must square that. And I land up with an answer of 100,000 newtons per coulomb. Let's think about the direction. If it's from a positive charge like that, it means that it is the field at point P is always from positive to negative. So in other words, it is going to go to the right, away from the positive, away from the positive towards the negative. So I'm going to say right. Then taking a look at the negative 6. Exactly the same formula. Substitute in 9 times 10 to the power of 9. Substitute in 6 times 10 to the negative 6. Sorry about that. And divide it by a distance. This time my distance is only 20 centimeters, so that's 0,2, and don't forget to square it. And I then land up with 1350123 newtons per coulombs, and it's from positive towards negative, so this time it's to the left. So I now have two vectors, one is to the right and one is to the left. So if I want the resultant vector, net electric field intensity, the net vector, the resultant vector, I go 1350123 minus 100,123, and I am left with 1250123 newtons per coulomb. Who won the race? The left won the race. It's bigger, and there you go. So it's really just a vector question, but with electric fields.